I will begin with a word of prayer. Heavenly Father, we thank you for this day. We thank you for the hurricane being a non-event for many people. We pray for the people that are still affected, that you'd help them get out of the mess. And I just pray that you bless this class today. Help us to glorify you, Lord, in what we do. Lord, in your name I pray. Amen. All right, so I think I had a result that I should prove. This has slipped through the cracks somehow, but it's kind of an important one. Here's the theorem. If phi from G to H is a group homomorphism, then phi is 1 to 1 if and only if the kernel of phi is just containing the identity. Now, you might recognize this from linear algebra, where we had this theorem as well for linear transformations, right? But the proof that I gave there for linear transformations is, in fact, really not a linear algebra proof. It's, in fact, a group theory proof in disguise. So here's the proof. So let's assume that phi is a mapping from G to H, where G and H are groups, and E is the identity in G, right? Also, we assume what? Phi of xy is equal to phi of x times phi of y. We'll use multiplicative notation for this proof, all right? So we're assuming that G is a function and that it's structure preserving, right? In other words, it's a homomorphism. All right, so there we go. That's the preamble. That's the backdrop. Now we can work on the proof. All the other part of it. So let's look at the forward implication. And so we're going to assume what? Assume that phi is 1 to 1, right? Assume it's injective. And then let x be an element of the kernel of phi, right? What's that mean about x? Phi of x equals to what? The identity, right? This is a property we proved for homomorphisms, right? I mean, I proved it for isomorphisms, but then I mentioned that, hey, this proof just as well works for homomorphism. So here it is, E. I'm sorry, but that's just definition of kernel. What I was just talking about was the fact that this is equal to what? This is also equal to phi of E, right? So this is a property of homomorphisms, right? A property you ought to be able to prove. Yeah? If I asked you to prove that, you got to be able to prove it, yeah? Anyway, so phi of x equals to E. What's this say then? Thus, x is equal to E, since what? Phi is 1 to 1, right? But we already know that E is in the kernel, right? And we just proved that any element of the kernel is E, so it stands to reason that the kernel is just what? The kernel of phi is equal to just the set containing the identity. What did I do? Nothing? Okay. Now, we can go the other way. What should we assume in the other direction of the proof here? If and only if it's biconditional, right? We have to prove both directions. So I think the other direction, we should assume that the kernel is the identity, right? The set containing the identity, be more clear. And then what? I'm saying suppose this. Let x and y be in G, and suppose phi of x is equal to phi of y. What is our goal to show then? Right, x equals to y. Now, notice that phi of x equals to phi of y. Well, these are both, where is that happening? That's happening in where? Where's the image of the output of the phi function is in H, right, which is a group. So this is invertible, right? Notice that this phi of x, phi of y, these are both, of course, elements of H. So the inverse exists. Phi of y inverse exists. And we have that phi of x, phi of y, parentheses inverse is equal to E, right? And I mean E sub H if you want me to be picky. The identity in H, yeah. Fine. Now I feel guilty. I'll go put a G sub here and an H sub here and add an H and put some G's. G, 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 G. All right. Yeah.
Would you expect us to do that like on the test, differentiate between identities?
Well, of course, it wouldn't be written, and you'd have to read my mind on that day whether to know or not, whether or not you're supposed to do that. So, sure. No, I mean, it depends on the proof. If I put that notation as part of the problem statement, I probably want you to use it. There exist problems where a confusion between which identity you're talking about could be sort of mission critical to making the argument, but not necessarily. I mean, in the same sense, I'm using multiplicative notation for both operations in G and H, right? I didn't insist on using like a star and a diamond or something more esoteric. These are customs. All right, so there's another property we proved, which is what? That is phi of y inverse, right? And then what? Which implies that phi of x y inverse is equal to EH, right? But what's that say about x times y inverse? Is an element of the kernel of phi, which, by the way, is E sub g. Thus x y inverse is actually equal to E sub g, and so x y inverse y is equal to E sub g y, which then gives me that x is equal to y, right? Which then implies what? X. So remember, we started out with phi of x equal to phi of y. We've gone through a string of deductions, and we've come to the conclusion that x is equal to y. This says, what about phi, since x and y were arbitrary points in the domain? This and that implies this. Therefore, phi is 1 to 1. And that completes the proof, because now we've shown both directions. Yeah. So my larger point to you here is if we have a homomorphism, right, and you want to show it's 1 to 1, it suffices to show that the kernel just has the identity in it. That's sometimes easier to show than just direct proof of 1 to 1, right? That was certainly the case in linear algebra. It's also the case here. Any questions? Yeah.
For the last line, instead of saying like xy inverses in the kernel phi, would it be okay to take the equation that's at the end of the line above it and then just do like phi inverse?
That would not be okay, because phi inverse doesn't even exist in general. I mean, it depends on what you mean by that. I mean, if you mean by that I can take phi inverse of both sides because phi inverse of EH is the kernel, and to say that phi inverse of phi, I mean, it depends on what you have. There's a sense in which that would be logical, right? But you should keep in mind that I will probably take off points because I don't believe that you guys have done the legwork to establish such identities which involve mappings of sets. For example, what's the case here? Which one of these is the identity? Actually, are either of those identity? What does that even mean? I mean, what I'm trying to get at here is these are not actually functions. So, you know, this is a notation. So when we write things about the inverse, when the inverse doesn't necessarily exist, they have to be understood in terms of images of sets.
You don't know that the inverse exists because it's not an isomorphism?
Right, we're just saying it's a homomorphism. So let's see here. For example, let's see here. How about, I don't know, let's see if this will work. If we wanted to go from Z6 to Z6, phi of x equals to 2x, does that define a homomorphism? In other words, is phi of x plus y? Well, that's 2 times x plus y, right? Which is 2x plus 2y by modular arithmetic, which is, by the way, phi of x plus phi of y. Yay, homomorphism. Is it an isomorphism? Well, no, certainly not, right? The kernel of, what's the kernel phi here? So can you tell me what the kernel is? Oh, here, I'll start us out. 0. What else? 2 times what is 0 in Z6? 3. Ah, yes, 3 is also in there, isn't it? That's it. But the point is that that's 2 things, right? So both of those things map to 0 under phi, which means that the kernel of phi is 0, 3. I mean, it's anyway, this mapping is not one-to-one, so phi inverse does not exist as a map, right? Phi inverse from Z6 to Z6 does not exist as a function, right? I suppose it does exist as a relation, right? But as a function, there's no inverse. Oh, this is as good a time as any to draw the subgroup diagram, subgroup lattice. So here it is. If this is Z6, right? What are subgroups of Z6? I found one of them right here, right? Kernel phi. How about kernel gamma? Let's let gamma be, let's say gamma of x equal to what? I like 2. How's 3 work? I mean, you can see that that's going to be a homomorphism as well, right? You can check it. It is. And what else? I mean, you should worry a little bit when I write down a formula, because what if different representatives of Z6 gave us different values, right? So to check this formula, to be careful, I should think about this in the more, you know, annoying notation. X sub 6 is equal to 3x sub 6, like that. And the question is this equal to, like, question mark, 3x prime sub 6 given what? X sub 6 equals to x prime sub 6, right? What does it mean that 2 representatives in Z6 give you the same class, the same element in Z6 is just what? X prime equals 2, x plus 6j, right? And so the thing is, when we look at 3x prime, what do we get? 3x plus what? Plus 3 times 6j, right? So the thing that the formulas, if you look at different representatives of the input, the corresponding outputs for my formula both yield the same equivalence class in the codomain. So the formula makes sense, is my point. Can you guys think of a number where it wouldn't make sense? Anyway. Okay, anyway, my larger point here was that this set is just what? This is 0, 2, and 4. This guy was when we started with 0 and 3. Are there any other subgroups of Z6? Yeah? Yeah?
0 and 1.
How about just 0 and 0 and 1? Just 0. Just 0 I'll take. Just 0. Just 0. Right? So 0 is the trivial subgroup, and that is itself a subgroup of these guys. All right? So we have this. This kind of diagram says things like, it says 0 is a subgroup of, 0, 2, 4, which is itself a subgroup of 0, 1, 2, 3, 4, 5, aka Z6, yeah? And on the other hand, this part of the diagram would say, hey, 0 is a subgroup of, 0, 3, which is a subgroup of C6, yeah? This is called a lattice diagram. So these are sometimes useful as you're trying to organize your thinking about like what are different possible things in the group you're looking at, right? It's not an unreasonable question to ask you guys to draw the subgroup diagram for the examples we've thus far studied. What are those examples? What would the subgroup diagram look like for, I don't know, let's look at, what do you guys want to do, D3, D4? What's your preference? D4, all right. So if we think about D4, what's it got in it? It's got E, A squared, A cubed, B, BA squared, and BA cubed, right? So first of all, subgroups that you've got. I mean, the stupid one, of course, is just the trivial subgroup, right? You also have the cyclic subgroup generated by A, which is also generated by A cubed. That's everything, this part of it, right? So you have a subgroup of order 4, the cyclic subgroup of order 4. There's also a cyclic subgroup of order 2 that's built just from the A's. What is it? This guy, right? That's another subgroup. Listen, every element that you can find that has order whatever, that's a subgroup of order whatever. Right? Elements of order 2, that's, in some sense, just a different language for a subgroup of order 2. But you should not confuse, those languages need to be precise in your test. Like, you're like, well, it means the same thing. Like, being fuzzy like that, it's not going to work for us, okay? What I'm sharing with you just now was an intuition. What you must write on your test is not intuition. You must write things that are actually true. All right, anyway. I know. What is here? E, B, yeah. And we also have BA, which is EBA. We got BA squared, which is EBA squared. We've got BA cubed, which is EBA cubed. Is there anything else? I don't think so. So we can make a picture of this, the so-called subgroup lattice diagram, and it looks like this. So we've got D4 up in the top, and then below it, you've got your cyclic subgroup generated by A, right? And then below that, you have the cyclic subgroup generated by A squared. Okay? And then on the other hand, you've got these four other guys over here. You got your B, your BA, your BA squared, your BA cubed cyclic subgroups of order 2, 2, 2, 2, 2. And of course, is this a subgroup of any of these? It is not, right? So down below here, we just have the trivial group, which is of course a subgroup of everything. And there you go. That's the lattice, the subgroup lattice for D4. Yeah.
So we can just leave A cubed out of there since it's equivalent to A?
Right, yeah. I mean, of course, you could also write this curly bracket A squared, A cubed. I'm just saving myself some writing and using, yeah. Anyway, this is kind of like small potatoes. I mean, I don't know what you want to say. This is not a big deal over this test. Like, we're talking about like not knowing this costs you 2% or something. Like, this is not what most of the test is about. It's just a new topic, so I'm trying to spend a little more time on it. Since I didn't assign a homework problem on it, right? Which makes it less likely to actually appear on the test, doesn't it? But anyway. Okay. So let me look at the solution mission 3 with you guys, if I can find it. So let's ask some fun questions. Prequel 1 is on, basic facts about integers and divisibility, the Euclidean algorithm. What of prequel 1 is most important that you should really know how to do for sure? The Euclidean algorithm. Very good. We have a winner. Prequel 2 is on modular arithmetic. What matters most from the prequel 2 on modular arithmetic, actually? What matters most is understanding what on earth this means and how we decide whether or not two equivalence classes are equal, right? And the actual proof that modular arithmetic makes sense. Those are things you should be able to take ownership of. We don't always get into those nuts and bolts, right, the last few lectures, because we like to work with Zn having 0, 1, 2, n minus 1, but you should remember those are shorthands for sets of integers, which we have a systematic way of adding and multiplying, right? All right. And of course, the merger of the Euclidean algorithm and finding inverses, right? That's something I've asked you homework questions about. Prequel 3 was on permutation. What matters? What's like the central calculation of that one? What's that? Yes, exactly. Understanding cycle notation. How about the order of an element as it relates to permutations, right? That's important. The fact that disjoint cycles commute, but not disjoint cycles don't, well, they might not commute, right? I mean, beware of the issue of disjoint versus not disjoint. Of course, the definition of even and odd permutations is important. What's the best way to prove that the group of, the subgroup of permutations, the so-called alternating group A sub n, is a subgroup of Sn? How would you prove that? Yep. say the kernel of Sn would be in the right spirit of what I'm looking for, but not the right kernel. I mean, we say kernel of a homomorphism. So like which, what you said Sn, what did you mean by that? But we talk about the kernel of a mapping, right? So it's the mapping of what kernel? Kernel of what mapping is An? Mm-hmm. So if you had told me that An is the kernel of the sign the sign mapping, which is a homomorphism between Sn and the subgroup plus or minus 1, right? Hey, where does plus or minus 1 live? Is that a subgroup of complex numbers, or is that a subgroup of real numbers? Or are those the units of the integers? Which one is it? Yes. It's all good. Right. Because I don't know. I mean, however you want to look at it, any of those contexts give us a set containing something we call minus 1, something we call 1, that behaves as a multiplicative group, right? All right. So, where was I? So, I mean, this is a good exercise what we were starting to do, which is to just go lecture by lecture and ask yourself the question, what was important from this lecture? Like, what should I know from that, right? What is expected of me here? You're like, to suffer. Fine, you got me. Guilty as charged. See here. Well, that one's sideways. I'm almost there, guys. I will, of course, post these in Blackboard soon. I might wait a little bit to post these because I have not yet completed the last homework problem because I have had an unending stream of people talking to me all day. And that's fine. That's good. That's why I'm here. But it's also why your solution's not completely written yet. So don't worry. It's just the one problem you're confused about. So any questions about mission 3 specifically? Like, you guys got no questions? That's good. Yeah.
I have a question from the video.
A question from the video. That is. That you can just ask.
Okay. So there was an example with Q8.
I think I have that actually. Well, I'm going to try to. All right, let's. I got to open this with the Adobe because it did this to me, and then I got to do one of these. Oh, come on, where'd you go? Rotate. Rotate. Oh yeah. All right. Good times. Let's see here. Oh look, there's what Bethany was just talking about. So that one. So you had a question about Q8. What have I done? Uh-huh.
So when you finished, it said that it was a subgroup of S4.
Oh, no. It should be S8.
Okay, that's what my question was.
Oh, well, okay, good. Yay.
Okay.
I could have. Oh. Any questions about this while I have it open? Do you guys understand the process of finding the Cayley representation of a group? If I was asked you to, it's a pretty mechanical thing. You just look at your group, pick an element, then you look at left multiplication by the element. It will go a certain path around the group, so to speak. All of those things form a cycle. Then you pick something else, continuing to multiply by that same element, and that'll form another. Eventually, you're going to exhaust the group as you look at different left multiplications. So like when I look at left multiplication by j, it takes 1 and moves it to j minus 1 minus j. When I look at I, the left multiplication by j moves it to minus k, to minus I, to k, and to I again. So we've got these two subsets of these quaternions 4 of those and 4 of these, and so there's basically 2 4 cycles that corresponds to the left multiplication by j. Anyway, I don't know, I think the blue notation's kind of cute, but you know, there you go, that's actually, and you can see that this is, goodness gracious, if I assign a problem like this on the test, I am going to enumerate the group elements, right? Because what if I didn't? How would you grade this? See, because this is just as well, I mean, you could relabel 1, 2, 3, 4, 5, 6, 7, 8, any different which way you like, and that would still give you a representation of the quaternion 8 group according to that other system of labels. Oh. I'm sorry, I was trying to talk about more interesting things. This is all Bethany's fault. All right. Oh, yes, here we go. So I guess you guys have no questions about this. That's right? No? Yes. The one I haven't worked, the last one?
Sure.
No, I haven't worked that one. This one, yeah.
Problem 30.
So everyone's good on the first problem, I guess? All right. So I have all of the gory details written out for you. Problem 22, you know, for problem 22, you know, the problem like this on the test, right? Suppose you're just stuck. There's something about thinking about the group being generated by A and having order 30, which is just, for some reason, unfathomable. Like, just, you cannot fathom it, right? One way you could sort of shake yourself loose of that would be to think about Z30, right? Because if you just start thinking about Z30, then all of a sudden it's much easier to see, oh, 15's got order 2, and it's the only one, right? 10's got order 3. It would be the only one, but if you think about 10 plus 10, I get 20. And wait a minute, 20 also has order 3. So 10 and 20 are the only things with order 3. Like, what has order 5? Well, 30 divided by 5 gives me 6. That's got order 5, right? And then you can start thinking about, well, what else has order 5? Then I have to actually think. Did I even ask about that? Oh, yeah, order 5. A to the 6 has order 5, and if you look at it, oh, well, that's going to generate a cyclic subgroup of order 5, which has prime order, which means that any relatively prime power to 5, in other words, 1, 2, 3, 4, those powers of my generator will also be generators, which means that a to the 6th, you know, to the square, cube, or 4th is also going to be an element of order 5. But anyway, my point to you is, if you didn't, for some reason, if you didn't understand this yet, and you were like, just for whatever reason lost on the test, you could actually stop and think about Z30 for a minute, and maybe you'd be able to find your way back to what to say here. Yeah. Just a thought. I want you to think this way, though. Yeah. So again, the key idea here is that if we have a subgroup of G and the order of the subgroup is M, with H being a cyclic subgroup, then if B is a generator, then there exists Euler phi function of the order of the subgroup, phi M, other generators. In other words, B to the J is also a generator as long as J is a unit UM, right? This M has no direct connection to the size of G, right? It's all about the subgroup you're in. Like, if you've got a subgroup of order 2, there's just one generator. We saw that actually over here. One generator, one generator, one generator, one generator, one generator every time, right? And if we're in a subgroup of order 4, like here, it doesn't matter if it's a subgroup of D4 or if it's just Z4 or if it's something else. Subgroup of order 4 has how many generators? If it's a cyclic subgroup of order 4. Well, it's got 2, right? Because phi of 4 is 2, because there are 2 relatively prime numbers to 4, yeah? What's the other possibility for a subgroup of order 4? What else could it look like? The Klein 4 group, right? Is the Klein 4 group cyclic? It is not. So theorems about cyclic subgroups do not apply to the Klein 4 group. Not to the whole thing, right? So. 23. So to summarize 23, basically you just look at these four cases. 2 of them have order 6. 2 of them have order 4. So your only possibilities are that groups of the same order can be isomorphic, right? So immediately your choices for possible isomorphisms are narrowed down to the 6 with 6 or the 4 with 4. when we look at the four, one of them's cyclic and one of them's not. So they're not isomorphic, right? Because cyclic groups are isomorphic. I mean, if isomorphic groups, if you have two groups are isomorphic, if one is cyclic, the other is, right? What are other things transported by isomorphism? Like order of elements, right? The number of elements of each order, those are transported by isomorphisms. If you have generators and relations, any relation must be transported, right? So then, on the other hand, U7 was actually cyclic with 3 as a generator, and the U14 is actually cyclic with with 3 as a generator, ironically enough. So the isomorphism defined by psi of 3 equals to 3, which is not the identity map. Really, to be more pedantic, that would be psi of 3 sub 7 maps to 3 sub 14, right? That mapping generates an isomorphism between U7 and U14, right? I say it generates an isomorphism. What do I mean? I mean that if you define an isomorphism like I just said, then it's clear how you would extend this, right? 3 to the k is what? So I mean, essentially, you just define the isomorphism by the rule of exponents. This is the analog of what I called linear extension in linear algebra. So if you fix the generator, and it's a cyclic group we're talking about, then you fix the whole map. All right, so that's that problem. Oh, what? No. This one, I hope you understood. That is a good problem. I gave a couple different paths to arguing that the order of G had to be a prime, all right? So you can look at those and decide which way you like more. Some of you may have just said, well, I'm going to construct an isomorphism from the given group to Zn, right? If you do that, then you could apply the theorem in the notes, which said that, well, the theorem in the notes say that if you had a curses. I'm forgetting. You showed me earlier, Samantha, the theorem in the notes. Which one was that? See, that's. Yeah. I'm not sure that theorem's in the notes, but let's go on. It's possible you have a different proof than this and it's still valid. Your proof certainly should have used the idea what? That if you pick an element other than the identity, it generates a cyclic subgroup, and that must be the whole group, because otherwise you'd have a proper subgroup which was not the whole group, which is forbidden by the data at the start, right? And then the other thing has to do with if A had anything but prime order, you could then look at the subgroup corresponding to the. We could use the fundamental theorem of cyclic groups to split off a subgroup of smaller size that wasn't the identity, if the order of the group was not prime. The fundamental theorem of cyclic groups would give us a subgroup which violates the data. Here's the problem 25. Basically, the point is just that, essentially, the whole thing really just boils down to the calculation right there at the top. That's most of it. If you really embrace that formula, everything else just kind of falls out of it. says that if we have a homomorphism of Zn to Zn, it's essentially fixed by what, I mean, it is fixed by whatever it does to 1, right? Because phi of k is k times phi of 1. That's the rule, exponent law. Anyway, it's a property of the homomorphism. And then furthermore, if it's an isomorphism, then it has to send generators to generators, right? So 1 is a generator of Zn. What are the other generators of Zn? Things in the group of units, right? So your choices are to send 1 to some element of Un, which means that there are Un, as many things in Un different choices of how to define an isomorphism on Zn. And in fact, that's essentially the isomorphism. The isomorphism is just to map the value of the automorphism at 1 to the unit, group of units, and that will define the isomorphism. So here's details. You know, I show it's a homomorphism, and then I eventually define the isomorphism between UN and the automorphisms, because I don't know, I just went that direction. You could go in the other direction, whatever. Psi of k is phi sub k, where that phi sub k is that means multiply by k, right? So it's well, I guess it's left multiplication by k, isn't it? Although that's not, a little bit misleading because we're not inside a group in that sense. Anyway, I shouldn't. All right. It's not October yet. We can't talk about rings. So, all right. Anyway, the point is this mapping psi, so defined, you can prove by this little calculation right here, takes multiplication in the group of units to composition in the set of automorphisms. Structure preserving, and then you can sort through it and prove, in fact, it's a bijection and consequently an isomorphism. So that was that one. Did you guys get anything else? I got these 4. Did you get these 4 symmetries? What did you guys get? Good. Just checking. I mean, I don't know. I always have this feeling with symmetries, like, did I miss something? You know? So, and for diamonds, I also got 4. You guys get that too? Although it's kind of funny, the natural presentation inside the permutation groups looks a little different, right? Did you also get something like that? Yeah, okay, cool. This one here, I often ask this question in one sense or another, like, you know, well, let me just a second here, I'll get on with it. Anyway, in short, there are elements of order 1, 2, 3, or 6, and there they are in D6. My question for you is, what if I asked for D600 on the test? Could you tell me the elements, what the possible order for elements was in D600? And could you tell me how many there was of each? Because that is a completely reasonable test question. Although I might want to make it like 75 or something not so huge, I don't know. So to summarize problem 28, your goal essentially was just to find matrices which behave as the generators and reproduce the relations for the dihedral group, D4. And so I figured out, I mean, I think there's more than one choice here, but this is the choice I made, that the I0, 0 minus I matrix has order 4, and this B matrix has order 2. And when I look at, you know, B, BA, BA squared, and BA cubed, I get the rest of that list. So these reproduce the thing, they satisfy the baba equal to the identity relation. And so if I make my mapping, map B's to B's and A's to A's in this sense, right, from the dihedral group to the H, then this should define an isomorphism because we're sending generators to generators of the same order, and we know that these generators preserve this, they satisfy the same relation, right? Now, you're like, well, that's just something you're saying, it's not something you proved. Here's an explicit proof that actually defines an isomorphism. I have it at the bottom of this page, all right? Now, if your solution didn't have this, it wouldn't be wrong because I gave you this theorem that if you map generators to generators of the same order and you preserve relations, if you check on the relations being preserved in the natural sense, then that defines an isomorphism, right? So you had that to work with. Suppose you didn't have it to work with. Here's how you could prove it. Just explicit calculation. Here's 2 arbitrary elements of D4, right? and then by the generator, by the fundamental relation, which is that AB is B, A to the JB is B A to the minus J. If you think about that, you can generalize it a bit and put minus 1 into the epsilon. That just becomes the number 1 when epsilon is equal to 0. So like that is the more general commutation relation, is that this is equal to that, if you want to. Yeah. I never said that in class. Not yet. Is this class? Yeah, okay, almost, just barely. So anyway, the point is with that, then you can use laws of exponents, apply the definition of the map, and then you just undo what you did, because the big B and big A satisfy the same relations, which allows us to undo the exponent manipulation I just did in the same way to undo them to get back to B epsilon 1 AJ1, B epsilon 2 AJ2, which is this. So you have that maps to that. That's structure preserving. A similar calculation is always possible if you map generators to generators and relations to relations. I'll let you look at 29 and 30 later. I figure you might want to look at last year's test for like 3 minutes at the end, right? Am I wrong? No? All right. Course evil? That must be course evaluations. Let's see here. And or some other form of administrative paperwork that I'm not interested in. Let's see here. All right. This was last year's test. Prove that's not a group under addition. Calculate the inverse of 76 mod 101. Fill out this Cayley table for Z9. Z9 star, that was last year's notation for U9. Find each generator for U9. Find all the elements in Z90 which have order 9. 9. Let phi be a surjective group homomorphism. Suppose G is a billion. Prove H is a billion. All right. You've got a group. You've got an element of order n. Prove that if the element to the power k is equal to 1, then that forces n to be a divisor of k, n to divide k rather. This problem was naughty. Problem 9, let the center of a group. Yeah, that was a bad problem. I thought if you twisted a standard problem a little bit, it would still be a reasonable problem, just moderately difficult. In fact, it's much harder. Anyway, digressing. So prove the center is a subgroup. Yeah. Prove the kernel. Let's see. What is this? Oh, prove the kernel is a subgroup. Yeah. Explain why AN's a subgroup. Show that SN is non-abelian. That was a homework problem for you guys. Oh, look. This problem 13 we talked about in the help session. Remember? You like this problem, Liam. This was your problem. Oh, that's it. There was actually a problem 14, but nobody did it, so I was like, yeah, whatever. I will post this for you guys, sure, but I think it's misleading because what you need to do is look at your missions and the lectures because that's more representative of for your test, yeah. Thanks, guys. Sorry about the grading on mission 2. The hurricane.